In Stats on Wednesday, we finished up this type O blood problem. We had already started this one. So a kid has a 0.25 chance of having type O blood, and this family's having 5 kids. Supposedly it's all independent, what type of blood they have. And we got down to, I believe, this part right here. And I just wanted to show you in words what it looks like to write P of x equals 3. So we could, now let me refresh you in case you didn't skim that paragraph. This is binomial, probability, or sorry, sample size is 5, and probability is 0.25 that someone has type O blood. So if you wanted, you could do it the formula way. 5 choose 3 times 0.25 to the third times 0.75 to the second. So that formula is on your formula chart, and you could do it that way. 5 choose 3 is tricky on the calculator. That's a combination. So you'd want to pick probability, then combinations. But there's a one-shot way to do it, and that is with binomial PDF. So if you press Menu, Stats, Distributions, and then scroll down to binomial PDF, or if you're holding an 84, press Second and then VARs, and scroll way down to binomial PDF. I picked PDF because it says equals, or it says exactly, and that's PDF. In just a second, the question right below this, we're going to use CDF. So N is 5, P is 0.25, X is 3, and let's see what we get. We get 0879. All right, the question changes at the end. No longer is it exactly, it's a more than. So x greater than 3. So we could do binomial PDF twice, but there's another function on your calculator called, and by the way, the reason we'd want to do it twice is because we need 4 and we need 5. But we could do binomial CDF. So if you have an Inspire, trials are 5, P is 0.25, lower is 4, and upper, I'm out of room, is 5. And that'll give us our answer. If you're holding an 84, you got to be a little clever with it. So let's type it in. And you get 0.0156. If you're using a TI-84, you can't change this lower bound right here. It's locked in as 0. So you got to be a little clever with how you use CDF. So you could type in an upper bound of 3 because 1 minus probability of 3 or smaller gives us the answer. So if you type in an upper bound of 3, you'll get 9844. Take that away from 1 and you have our answer. So that's only if you have a TI-84. If you have an Inspire, you can do it the way I just wrote and get it outright. Okay, moving on. Should the parents, I forgot to answer. Should the parents be surprised if more than 3? So yes, they should be, because P is less than 0.05. This would be a significant probability. It would most likely cause them to doubt the original rate of 0.25 or maybe even independence. But ultimately, compare your probability to that 5% significance. So, All right, now moving on. There's our formula. That's on your formula chart. So that's what I was writing into earlier. And now we're going to move on to another type of problem where I think we're going to have to get the mean. So in this problem, there's this fast food restaurant marketing, trying to get people to come in and maybe get a free lunch. 12 basketball players show up, and if you push a button on the screen, it draws from a standard deck. So hopefully, if this was on a FRQ, they would define the standard deck. It's 52 cards, 4 of each type of card. So if you get a 3, a card with a 3, you get a free lunch. So probability of success for one person walking up to this screen, probability of winning a lunch is there are 4 3s in the deck and there are 52 cards in the deck. We're talking about 12 players, and we have to trust that this computer program is doing independence. In other words, it's resetting every single time someone walks up to it, shuffling the cards, whatever. Therefore, it is binomial. And we want the probability that 2 of them get a free lunch. So that's a quick one. That's binomial PDF. So try that out real quick. So it's not a super high probability, but I got 1754. And by the way, when you work one of these FRQs, you have to define the distribution and write the question. So here's me defining the distribution, and here's me writing the question, and then the answer. So those 3 things are required. All right, part B, or the next question, they make it a little bit harder to do by hand, but we have our handy calculator. Our sample size goes up to 250, and the question changes big time, fewer than 10. This would be quite a pain to do by hand. There is a trick where you can approximate it to the normal curve, but we're just going to use the binomial distribution on this. We'll maybe look at that approximation later in the year. So this is difficult because you need to get the probability of 0, of 1, of 2, of 3, of 4, all the way up to 9, or just use binom CDF. So trials are 250. P is still 4 out of 52 for each customer. My low is 0, so the TI-84 can handle this easily. And the upper is 9. Careful not to type a 10, because we don't want to include a 10. We want fewer than 10. So if you're holding a TI-84, you're just going to type a 9 for your X, because that's your upper bound. If you have an inspired, type it just like I wrote it, and we get a pretty small probability. It's just probably not going to happen. A lot of these restaurants and supermarkets and stores, they like to market things, but chances are they're not going to give out many free things because it's unlikely in this situation. All right, I think next is the mean and standard deviation of a binomial distribution. It's almost too good to be true. It's just sample size, or trials, times P. Standard deviation is almost just as easy. So let's give it a shot with this tap water problem. People are doing a taste test to see if they can determine if the water is tap or bottled. And we're letting X be the number of correct guesses. So we need to define it as binomial. So this is a check. it is a binary situation. They guess right or they guess wrong. Independent, we're assuming in this class of students, no one student is helping another student. So each student's guess is independent. There are 21 students in the room. It's fixed. We're not doing this infinitely. And probability, if they're guessing, is 1/3. And it does say that. So we're assuming they're guessing. So we find the probability, or the mean, by going 21 times 1/3. And we can do that in our head. We think about 7 of those students are going to guess correctly. Standard deviation times its complement. And we get 2.1602. Hopefully that's pretty easy. So let's wrap this problem up. Of the 21, 13 made correct identifications. Am I convinced that students could tell bottled water from tap water? So here's the question. And this question is quite the loaded question. I mean, we have to think quite a bit about it. First, we're going to do binomial PDF. And we get 0.0050. This is way unlikely. But remember, we're assuming guessing with this. So in a way, this question is testing whether or not, like they run the experiment and we compare it to this probability and it's testing whether or not these students are guessing. Because if they're guessing, let's write this out. If guessing, it is very unlikely that 13 will guess correct. It should not happen. 0.5% chance of that happening. Therefore, how did they phrase it? Usually use their words. His students could tell bottled water. It is likely the students can tell the difference between bottled and tap. So big question. They bring this concept up: testing, guessing, testing equally likely, testing a majority. Sometimes they bring politics into this. So we'll see more problems like this. All right. See y'all later.